Okay, so this is a re-record of the first little bit of the exam review. I think it probably was maybe about 10 minutes before I realized that it was not recording. So we're just going to go back through this part quickly. And so before what I started going over, Ilham had a question about when the kinetic energy is equal to the potential energy. And so we looked at this example of something going down a ramp from A to B to C, and then back up a ramp from C to D to E. And so I said, let's say this object that is rolling along this ramp has a weight of 10 newtons, and it is initially at some height h, which we'll say is 10 meters. So if it's initially at rest, then all of the energy it has available to it is potential energy. And so we're going to assume this is a smooth, frictionless ramp. And so friction does not do any work on the object. And also the normal force is always perpendicular to the displacement of this object along the ramp. So it doesn't do any work on it, nor air resistance. So it doesn't do any work on it. Any non-conservative forces we can think of are not doing work on this object. So mechanical energy should be conserved. So if it only has potential energy at point A, then the available energy it has for this entire trip from A through E is just the initial potential energy, which is mg, the weight of the object, which I just gave the weight as 10 newtons, times the initial height, which is 10 meters. And so that's 100 Newton meters or 100 joules. And so that is also, since it is at rest, our total mechanical energy, because the kinetic energy is 0. Then we skipped ahead to point C. At that point, we have lost all potential energy in this object because it is at this baseline. It cannot go any lower as far as this system is concerned. So that is a sensible place to talk about the baseline 0 potential energy for this system. And so for energy to be conserved, that means all of it must have gone to the kinetic energy. That's what tells us that the object is going to be moving fastest at that point C. But still, the total mechanical energy is the same, that total 100 joules. So then we can answer the question of when is the kinetic energy equal to the potential energy? And so it is exactly when half of the potential energy is, or half of the total mechanical energy is potential energy and half is kinetic energy, so that they are equal to each other. So potential energy is half of its initial value when the height is half of what it was. So it should be, if the initial height was 10 meters, and that's when we had all potential energy, having half as much potential energy happens at 5 meters. So that's what we call point B. And so it is evenly split between kinetic and potential. And from that, we could figure out how fast this object is moving if we wanted to, since kinetic energy is 1/2 mv squared. And we could backtrack, find the mass of this object, which is roughly 1 kilogram, since G is 9.8 meters per second squared. Then the other useful thing about conservation of mechanical energy is that we immediately know on the other side that the energy split is exactly the same. That point D. Doesn't matter what the shape of this ramp is, doesn't matter how the slope changes through it. As long as we're at the same height and total mechanical energy is conserved, we immediately know that the energy is split the same way at point D. And then we didn't write point E, but we should know there is where it stops if that is at the same height. I'll try to drop at the same height as point A. And so all kinetic energy is gone. It's all been converted back to potential energy. Total mechanical energy is still 100 joules. And so we see that as the object moves from A to B to C, it's losing potential energy, gaining kinetic. As it moves from C to D to E, it is losing kinetic energy, gaining potential energy. But the total mechanical energy, the sum of those two things, kinetic and potential, is always the same throughout the motion, assuming again that no non-conservative forces like friction, tension, normal force, interactions with other objects do any work during this motion. And that is the point at which we moved into just covering or reviewing the notes quickly. So the big takeaway on this page is that the two main things that friction depends on are the materials of both objects that are in contact to generate that frictional force, and then how hard they're pressed together, which is given by the normal force that either object supplies on the other. If we could talk about the normal force either supplies because of Newton's third law, one pushes on the other with that normal force, the other must push on the one with the same normal force magnitude in the opposite direction. So the important thing about static friction is that it varies depending on how hard an object's being pulled on. So we talked about this example with the block. If you're not pulling on it at all, then friction does not need to pull back any. So the frictional force in that case is 0. If we pull a little bit harder, friction pulls a little bit harder the other way. We can keep pulling harder. Friction will keep pulling harder up until some point where it can't. The block and the surface can no longer muster enough friction based on sliding over each other, those intermolecular forces we talked about, these microscopic contact points. They can't muster any more friction than that maximum value, Fs max. And so if we pull any harder than that, then the object will start to slide and we enter the domain of kinetic friction, which we'll get to more in a minute. But that says that friction, the static frictional force can have magnitude anywhere between 0 and the maximum static frictional force. If it is at its maximum value, that's where we talk about using that it's equal to the coefficient of static friction times the normal force. The other thing I pointed out here was in problems where you've got a block or something else on a ramp, which we end up going into more detail on a little bit later in the review. It's important to remember that the weight of the object always acts straight down. So I'll draw over this ring. This is the weight of this object. It acts straight down towards the center of the earth, not into the ramp. What does act into the ramp, this perpendicular piece, is the component of that weight that acts along that. So we can decompose the weight vector into components that act perpendicular to the ramp and parallel to it. The component perpendicular to the ramp pulls block towards the ramp, and that's what's balanced out by the normal force, which normal means perpendicular. The normal force is always perpendicular to the surface that supplies it, in this case, the ramp. So it does not act straight up. As a result, it's not balancing out the full weight of the object. It's just balancing out that component mg cosine theta. And so it is very important to remember the normal force magnitude is not always equal to the weight of the object. It depends on what other forces are acting and what their directions are based on what object that the object of interest is interacting with. The frictional force, on the other hand, so if we're talking about static friction in this case, we're saying that the frictional force is just enough to balance out this component right here of the block's weight, mg sine theta. And so if this block is at rest, the magnitude of Fs is exactly equal to that component of the weight of the block, mg sine theta. And if, for instance, the block were being pushed up the ramp, friction would act the opposite direction. It always opposes motion, relative motion between the two surfaces. That's the main stuff from there. So it's important to remember that is the only two things that friction depends on is the materials of the two objects and how hard they press together. And again, for static friction, how hard it is, how hard the object is being pulled on determines how hard it has to pull back. So you don't need to memorize, for instance, this table of coefficients of friction. Anything like that would be given to you. And also you don't need to worry about more complicated examples like walking, where you have the direction of friction changing because the relative motion of this guy's foot and the ground is changing. It is going to be a good idea to look at at problems like this, where you are drawing in your free body diagrams and analyzing these problems. So it's good to look back at, for instance, this one where we talked about the synovial fluid. There aren't any problems that have you do something with friction forces and then something with kinematics. So kinematics is not strictly required on the exam. There are some problems that you could potentially use kinematics on, but there is, for all of them, the alternative of using things that we have talked about for this exam. So the end of chapter 4 up through chapter 7. And I believe that's where we picked up when I remembered to start the recording. So good luck. If you have any questions, feel free to email me, and enjoy the rest of the video, or as much as you can stand to watch before you fall asleep. All right. Here. Okay. I may need to re-record that first part, but from here on, it is recording. So back to this. Okay, so in examples like this, you want to be able to draw your free body diagram and know that the friction opposes the motion or intended motion. Whether you're dealing with a problem where the object is sliding or is not yet sliding, either is fair game. And that is the main things on friction, just knowing how to draw your free body diagrams when you're dealing with static or kinetic friction, and how to draw your free body diagram for something on a flat surface or on an incline.
Can you please draw these 3 states when the body is on the begin, like on the top of the ramp and the bottom, and when it's flat?
Okay, so we've got.
Thank you.
Friction, free body diagrams. So if we've got an object at rest on a flat surface, what forces are acting on that object?
Normal force perpendicular to the surface.
Yep.
And weight.
Yep.
Perpendicular to the surface, but yeah, the opposite side.
Yep. And is friction acting?
Horizontal but negative side.
Well, if we're not pulling on the block, is friction acting?
No, 0.
Yep.
There's no friction.
Yeah, so we'll say no pull. Now we'll do at rest pulling. So say our pulling force, the force we're applying by pulling is P. I'll say we're pulling this way. Well, does the normal force and weight part look any different here?
Yeah, they're the same.
Nope. Yeah, they are the same. And in this case is where we have friction acting the other way. What kind of friction?
Static friction.
Now, it's not necessarily the maximum static friction, it's just whatever it needs to be to oppose that pull, up to, if you can pull hard enough, eventually the static friction will reach its maximum value and can't supply any more friction. So that's the case where we have on the verge of slipping. So if you pulled even just a tiny bit harder, this block would start to slide. Maybe I'll say sliding instead of slipping then. So we pull hard enough. That's the most friction that that surface can apply, and the block. Get the normal force, weight. Okay, so what do we label this friction vector over here?
Static friction.
Not just any static friction, but
Maximum.
the what?
Max.
The
Max.
maximum. And in that case, and only in that case for static friction, that's when we can use this. For anything up to that, it's just opposing that pull P. So that static frictional force has the same magnitude as P so that the block can stay at rest. And then if we pull even harder, got the block sliding along. Okay. And nothing's changed in the vertical direction. And so what happens once the block starts sliding as far as friction is concerned?
We have the kinetic friction.
And its magnitude is typically what compared to static friction?
It's the same, but instead of mu static, it's mu kinetic.
That's true. And so how does mu kinetic compare to mu static typically?
Is it smaller?
It's smaller because it is easier to get something or to keep something moving, to keep it sliding, than to get it sliding. And that is because the friction force drops off once something starts sliding. So I'm going to draw this vector a little bit shorter. This is kinetic friction. And in all cases, the force of kinetic friction, its magnitude is coefficient of kinetic friction times that normal force magnitude. So you might notice I'm not automatically writing that that is equal to mu times mass times acceleration due to gravity, meaning I'm not saying the normal force is equal to the weight. That's not always true. An example of that is when something's on an incline. So we'll go in and do incline. I may not go through every one of these cases again because it's similar other than what's going on with our vectors, but okay, we've got something on an incline. It's some angle theta. Oh, is there a difference with pushing and pulling? For some reason, it's not popping up. I see these. But is there a difference between pushing and pulling for all calculation purposes? No. If you have something pushing on something, it's just the same effect as pulling on it with the same force in the same direction. That is a good question, actually. And it helps us draw our free body diagrams because sometimes you'll see like you're pushing on a shopping cart or something. And so it has a picture like this, but you want to draw your free body diagram for this thing. So you've got all the vectors leaving that point we used to represent that object. So we're pushing on it. It's got its own weight, normal force, and then say friction's opposing its motion. Not capital F. Okay, say it is moving, so kinetic friction. We'd like to draw our free body diagram with all the vectors leaving that point instead. So all the others are drawn that way, but we can move that force from pushing. Well, that really got out of hand. We can move it so that its tail does come from that dot representing the object. And so it's just whatever way we draw these that's convenient. And so we try to shift them all to so they're leaving that dot. But you see how it's the same magnitude and same direction. I just drew it leaving the dot instead of pointing to it. So that's the difference between a push and pull, is just whether it's the tail or the head of the vector that's pointing at it, but you can always change it from one to the other. It has the same effect. Does that clear up that question, Deja?
Yes.
Okay. Okay, so back to, we've got this block on an incline. So what forces act on this block? If it's just sitting there, so we'll say at rest and no, I'll say external, no, not external. No, we'll just call it no pull.
Normal force.
So all the forces, that's good, okay. So which way does the normal force point?
Really?
What was that?
Perpendicular to the ramp.
Normal force, normal means perpendicular. That's why we call it a normal force. It's always perpendicular to the surface that's applying it. So what's applying that force to this block is the ramp. So our normal force is perpendicular to the ramp. Then we've got weight, gravity, like Kendron said. Which way does that point?
Downward.
Straight down. So we draw it straight down, always. What a lot of people will do is say that's gravity. That is wrong. It does not just suddenly change direction because we have an incline. It always points towards the center of the earth. So we'll do that. So if this block is at rest, does a frictional force act in this case?
Yeah,
The answer is yes. Why?
because the object is sliding.
It's at rest. So it's not sliding. It is at rest. But
Is it like a frictional force that is keeping it in its place?
yes, what is wanting to pull it down the ramp?
Is it kinetic?
So kinetic refers to, kinetic friction, no. So it's not sliding. So we're dealing with static friction, but there is something wanting to pull it down the ramp. Yes, gravity. And it's not the whole force of gravity, but we can see how much of that force of gravity is pulling it down the ramp by breaking it into components that are perpendicular to the ramp and parallel to the ramp. And that's what we usually end up calling our, respectively, the perpendicular is the y-axis, the parallel is the x-axis. I'll draw that free body diagram in a second, although this is pretty much a free body diagram. And so if you're given that angle theta, again, this angle, because of geometric reasons, is also theta. And so since the magnitude of that weight vector is mg, the magnitude of this scalar component is mg cosine theta. And then this one is mg sine theta. So this side is adjacent to the angle, this side is opposite. And so if you do some rearranging after doing the trig, you'll get that their lengths are mg cosine theta, mg sine theta. So it's that component mg cosine theta that balances the normal force in this case so that the block does not move perpendicular to the ramp, so away from or toward the ramp. As far as parallel to the ramp, that component of gravity, that component of the block's weight is wanting to pull it down, mg sine theta. What's resisting that pull down is the force of kinetic friction back up the ramp. Okay, so in this case, what's happening along the along the ramp is that component of gravity is pulling down, and then the force of, sorry, that should be static friction. Force of static friction is pulling back up. And you can have heavier and heavier objects. So you're increasing that component of gravity acting down the ramp up into a point where you are dealing with the maximum static frictional force. So you could have something pulling and not making it go all the way, or not exceeding that maximum static frictional force, but I'll just jump to the case where we are on the verge of sliding. So we know that weight is still acting straight downward. We know that that normal force is still acting perpendicular to the surface. And really all that's different here is we're saying that this block is heavy enough now that it does equal the maximum static frictional force that the ramp and the block can supply. So you notice I drew my weight vector a little bit bigger here. This is a heavier block. It has a larger component acting both, draw that a little straighter, both perpendicular and parallel to the ramp. But the part that's going to pull it down the ramp is that parallel component, the mg sine theta component. And this is just what's balanced still by that normal force. So otherwise, or this is pretty much the same as the previous drawing. The only difference is we're on the verge of sliding, meaning that we're using the maximum static frictional force. And just like before, that is this. But is the magnitude of the normal force equal to the weight of the block in this case?
No.
No. Why is that?
Because the block is heavier?
Not because the block is heavier.
Is it because it's perpendicular?
It's because all the normal force is, yes, is perpendicular to the ramp. So what it is going to be balancing to keep that block on the ramp is just whatever component of gravity acts perpendicular to the ramp. So maybe if we do break off into a separate free body diagram here, we've got weight, normal force, our maximum static frictional force. Those are meant to be perpendicular. Didn't quite do a great job of that, but we'll go with it. So we said that we have a lot of forces acting parallel and perpendicular to this ramp. So that's where it's going to be convenient to define our X and Y axes. I'll call down the ramp positive X and up the ramp negative X, but that is entirely your choice. Call perpendicular outward from the ramp positive Y, and perpendicular towards the ramp negative Y. And we're seeing that this angle is also theta, right? That's this angle right here. And that's where we break the weight vector into its two components along the two axes. So that's mg cosine theta. Down that we've defined our direction, the component there is a negative mg cosine theta because it's acting in the negative y direction, and then this is a positive mg sine theta because it's acting down the ramp, the positive x direction. So if we want to find the magnitude of that normal force, eventually you do this step so many times that you just get used to doing it and know what the normal force is going to be. But what are the forces along the y direction?
The normal force and the negative g cosine theta.
Negative mg cosine theta. And all of that should be equal to what?
0.
And why 0?
Because there's like the block's not moving in the y direction.
Mm-hmm. And to be neurotic about it, it's not accelerating in the y direction because it is at rest as far as the y direction is concerned. And so in this case, you've got that the normal force is mg cosine theta, and then you have that Fs max is mu, mu s mg cosine theta in that case, because that's mu times the magnitude of the normal force. Okay. If gravity pulls down any harder than that, that component mg sine theta is any larger than this, then the block will start to slide down the ramp. And in that case, we have sliding, and I'm going to go fast through this part because it is almost the same. It's just what we said everything equal to at the end that changes. Got a block. Got weight. Okay, good. No questions so far on that I've missed. Normal force, and if it's sliding down the ramp, which way is friction acting and what type of friction is it?
It's parallel. It's parallel to the ramp, and it's kinetic friction.
Yep. So parallel to the ramp, so acting up the ramp, and it's kinetic friction. And there is nothing else pulling the block down the ramp. It's just that component of gravity. If you have someone that has like a rope attached to this block that's pulling it down the ramp, that is another force you need to add. But right now we're just saying, what's the block doing without any outside interference? So sorry, Deja, I couldn't exactly hear you. Could you repeat that?
When you just said if someone had a rope pulling it down the ramp, there would be another force. What force would that be?
So that would be if someone's pulling with a rope down the ramp, a rope transfers a force through tension. So that would be acting, that should really be down the ramp. I just didn't draw it quite parallel. So if someone were pulling, we'd have a force like that acting down the ramp in addition to everything else that's going on. So there aren't any quite like that on the exam. We usually do, or the questions do mostly stick to things closer to this. But that is something that could happen and has happened on homework problems, I think. So we said that if we, well, this angle is going to be theta. You could figure that out every time with geometry, but it's just if you know the incline is an angle theta, that angle between the component of the weight acting perpendicular to the ramp and the weight itself is also theta, whatever that theta is. Okay. So if it's sliding down the ramp, we have really two cases here. It could be sliding at a constant velocity or accelerating down the ramp. And that determines whether we set this whole thing, these net forces down here, to 0 or to MA. Okay. So if sliding at constant velocity down the ramp, And are you seeing that it really is not helpful to try and memorize this as all these sets of different cases? It's just I am reasoning through why I should have certain forces acting and why I should set something to 0 or MA. That's what I want you to work on, is not memorizing all these cases, but seeing how we can determine which case we're dealing with by looking at what the problem's asking for. So free body diagram here is, well, we can really use our previous one. So use this. The only thing that changes is we're dealing with kinetic friction instead of static. So I guess just for future use, I'll draw it in real quick. Fn weight. Kinetic friction in this case because it's sliding. And then we said it's convenient to define our axes perpendicular and parallel to the ramp. And we've still got our components of that weight acting towards the ramp and then down the ramp. And that now is, since we've defined our directions, let's say that's a negative mg cosine theta. This is a positive mg sine theta because that angle right there is theta. So if the block is sliding down the ramp at a constant velocity, it's not accelerating. So it is in equilibrium. And so that's an equilibrium case, because if it's sliding down the ramp at constant velocity and not moving into or out of the ramp, that says that it is not accelerating in the X or Y direction, okay? So usually if it's saying it's sliding down the ramp at constant velocity, you can immediately assume that means both the force in the X and Y directions are 0, because if the force in the Y direction, the net force, was not 0, we would have this block shooting into or out of the ramp, and we don't really see that happen so often. So in this case, we've got the net force in the Y direction is, what do we have?
The normal force and the negative mg cosine theta.
And that equals, what do we say? 0. So not accelerating in the Y direction because it's not leaving the ramp. Okay, and so again, the magnitude of the normal force is mg cosine theta. And then in the X direction, we've got what forces are acting.
The kinetic friction.
Okay, and what else? Acting parallel to the ramp. What was that, Ilham?
I think that's it.
You don't see anything else on our free body diagram that goes in the positive X or negative X direction?
The positive mg sine theta.
So it's a component of a force, but that's what we're looking at, is the net force components along these two directions. Okay, and minus the force of kinetic friction. No, not vector arrow, dealing with magnitudes. And so if it's sliding at constant velocity down the ramp, what is this equal to?
0.
0. Not accelerating down the ramp. And so we can determine, for instance, that means Fk which is mu k Fn always is in this particular case equal to, so this is always, in this particular case is equal to mg sine theta. So that's this case. And Fn itself is mu k times, or Fn is mg cosine theta. And so those cancel. And so we could, for instance, see that mu k is tangent of theta. What that means is, if we remember when I was dealing with the, like, lifting the block of the, excuse me, not the block, the like laptop stand with a wooden block or a rubber block sitting on top of it, we saw that it would start to slide at a certain angle. That angle is, and we would see this for the maximum static friction as well, that angle is related to the coefficient of friction. Okay, so we can say if it starts to slide at this angle of theta, then our coefficient of friction, kinetic friction, is mu k. Okay, and now the other case is for sliding, accelerating. Let's say down the ramp in this case. The free body diagram is exactly the same. It's just the net force in the x direction, which is still mg sine theta, minus that force of kinetic friction, is now equal to what?
mg.
Not mg. What law tells us the relationship between net force and acceleration? Yep, ma, so that's Newton's second law. Net force is mass times acceleration. And so in terms of components, is that, yep, Kendron, that's right. In terms of components, max and may. But in this case, ay is still 0 because the block is not leaving the ramp. Okay, so this is max. Whatever that acceleration is, it might be that we're solving for that acceleration. It might be that we're given that acceleration and want to find something else. But because the block is accelerating, and in this case is accelerating down the ramp, we use this. If it were accelerating up the ramp, it would either make sense for us to define our positive direction up the ramp and give signs accordingly to stuff, or we could call our acceleration a negative ax. Okay, so again, you see all these cases are just reasoning through it from drawing your free body diagram. That's the important piece, not trying to memorize every single one of these. So that is, I think, a pretty good coverage of friction. So we'll move into uniform circular motion. Once I figure out how to get back to those, there we go. So uniform circular motion, it's good to know the relationship between the period of a uniform circular motion, the time it takes for one complete revolution, and the speed of that circular motion. And that's just the circumference 2 pi r over that period t. And that's just an example of that, which, by the way, now that we're doing rotational kinematics, do you recognize what 830 revolutions per minute is telling you?
Are you referring to today in class when we had to do the radians?
Yep. Yep, so what quantity has units of revolutions per minute, or that could be the units for it? Angular velocity, a certain angle or change in angle over time. Okay, so there is a relationship between this tangential velocity, tangential speed in this case, and angular speed. Angular speed is the rate of rotation. Tangential speed is the distance something's covering over time. And we'll see what that relationship is later. But just thought you'd like to see that we have already actually talked about rotational motion, rotational kinematic stuff. You don't need to know how to derive the centripetal acceleration. What you do need to know is its magnitude and direction. It is always acting towards the center of a circle for uniform circular motion. And its magnitude is v squared over r, that tangential speed squared over the radius of that circular motion. And so I think this example right here is a very good one to look at and make sure you understand how we got those numbers. It's also good to know if you're going along a straight path at a constant speed, what does that say about your acceleration?
Zero?
Zero. But if you're going along a curved path at a constant speed, is your acceleration zero?
No, it's changing.
No, because the direction is changing, right?
Yeah.
Okay, so that's the big kind of takeaway for centripetal acceleration, is that something is accelerating if it's moving at a constant speed through a curve, because its direction, the direction of its velocity is changing, even though its magnitude, the speed, is not. Centripetal force is, again, it's not its own kind of force. It's just the net force acting towards the center of a circular turn or circular path. And so it is really just, if we look at all the forces acting on something and look at specifically the ones acting towards the center of a circular path, or the net force acting towards the center of a circular path, that is what we call the centripetal force. And so Newton's second law still applies. The net force is the mass times acceleration. It's just in this special case of uniform circular motion, the centripetal force, that net force towards the center of that turn is the mass times the centripetal acceleration. And so you can have a lot of different things supplying that centripetal force, or combinations of forces. So for a turn on a level curve, it's static friction that does it. If you're spinning something around like this plane, it could be tension. You're spinning it around at the end of a string. If you're on a banked curve, it could actually just be a component of a force, in this case, the normal force. And it could be gravity that is acting towards the center of a circular path to supply that centripetal force. And we can see that each of those types of forces has their own consequences. So it is good to know when to apply these equations. You don't really need to know the most fundamental equation you need to know for this topic is that right there, that the net force acting towards the center of a circular turn, which we call the centripetal force, is equal to the mass of the object doing the turn times its centripetal acceleration. And its centripetal acceleration is v squared over r. Everything else is just a consequence of that. So all of these things are things you could figure out from a free body diagram. But I believe, so there is not one that is on banked curves. So don't worry about knowing the specific formulas for banked curves. There is some stuff on satellites. So let's see. I think just this whole section on satellites is good to familiarize yourself with, except this right here is sort of an, I don't really know how to mark this to say don't do it, I guess. Don't worry about that. But this example right here with the Earth orbiting the sun, so you change the mass of the object that's being orbited, is a good one to look at. And then don't worry about this whole page on centrifugation. That was just a, hope you find this interesting as someone who will probably be using a centrifuge. Okay, so that is topic 5. So any questions on that before we keep moving? Okay, not seeing any questions. And again, we can do more practice problems after I go through. I just want to make sure this part is done first. So that's that chapter. Then there's topic 6, work and energy. The big thing here, it's good to know whether positive, negative, zero work means increase, decrease, or no change in speed. But the biggest thing is knowing the relationship between net work and the change in kinetic energy. So that's the work energy theorem, right? I guess that's, I've been using green. The work energy theorem you want to know, and then the consequences of the work energy theorem. So the work energy theorem says if you have a net force that's doing work on an object, or if you combine the work done by all forces to get a net work, that is what changes the kinetic energy of the object, which kinetic energy is 1/2 mv squared. You want to be able to apply that to say, find the net work on acting on something and find its resulting change in kinetic energy. So this is a very good thing to know right here. But it has 2 other ways we can write it, essentially, depending on the forces involved and whether they're conservative or non-conservative. So can anyone tell me what a conservative force is versus a non-conservative force?
Conservative force does not depend on the direction, or I can't remember. I think that's it.
So not quite the direction, but the path that the object takes.
Yeah,
So-
and the conservative don't. Well, it does depend on the direction of the path.
Other way. So conservative does not depend on the path. Non-conservative does depend on the path. And so can anyone give me an example of a conservative force?
Gravity.
Good. Okay. Any others that you can think of that we've actually used or dealt with? Normal force is actually a non-conservative force. Answer here is that gravity is the only conservative force we have done anything with so far. The relevance of that is that for conservative forces, you can define a potential energy. For gravity, that potential energy is mgh. And if we kind of go through this, so I guess as far as what to focus on, this example is probably a little bit more involved than anything you really need to worry about. I think this example is a good one, as is the weightlifter. So that's for just calculating work. You want to be able to use the work energy theorem to calculate a change in kinetic energy, though. So could be good to look at this one, but it won't be something quite as involved as this one was. Okay, so the big thing with work energy theorem and gravity is that gravity has a potential energy associated with it, and that lets us get all the way down to this. So this was all explaining conservative versus non-conservative forces to get to this idea of the conservation of mechanical energy. You want to know when it applies, meaning that the net work done by external non-conservative forces is 0, and then how to apply that to problems. So this example is really good for that. And then conceptual is also good to know that if you have a force acting perpendicular to a displacement, then the work done by that force is zero, and so it cannot affect the conservation of mechanical energy. So this is really, I think, the big thing to focus on is applying conservation of mechanical energy, but remembering that it is a consequence of the work energy theorem. And so in cases where you can't apply conservation of energy, you can still always apply the work energy theorem. It's just useful to use it in this form instead of the one from earlier, because this separates the non-conservative forces and the work done by them from the conservative force of gravity, because that's built into this difference of potential energies. So you want to be able to apply conservation of energy, and then when energy is not conserved, use this version of the work energy theorem. And so these two examples actually are good for both, since in the first one, we have only conservative forces doing work, and in the second one, we have non-conservative forces doing work. The rest of this chapter, this topic, power, conservation of energy, work done by a variable force, don't worry about it. Okay, impulse and momentum. I guess before moving on, any questions on that? Meaning topic 6, this previous stuff of work and energy. Okay, so then we got into, all right, there's one short blurb of work and energy. Oh, of impulse. Impulse is a force acting over a time. So while work is force acting over a distance, impulse is force acting over time. While work changes kinetic energy, impulse changes momentum. And that's why we have the work energy theorem and the impulse momentum theorem. They are very closely related, but they're both useful in that sometimes to solve a problem, we need to use both conservation of mechanical energy and conservation of momentum. And we saw some examples like that near the end of this topic. So let's go through real quick. So just remembering the impulse momentum theorem that says if you have an impulse, that changes the momentum of the object that the impulse acts on, and how to find different things based on that theorem. So these examples we did, all good examples. And then like with the work energy theorem, you want to remember what the not work energy theorem, the conservation of mechanical energy. You want to remember for the conservation of momentum, what its requirement is, that the average external net force, really when you're thinking about it, don't worry so much about average, but the external net force acting on a system is 0. So if all forces from objects outside the system acting on the system either are 0 or add up to 0, then the total momentum of that system remains constant or is conserved. And a system is, again, just a collection of objects, whatever objects we're interested in. We've only done a collection of 2, so that's all you need to worry about for an exam, but you can apply this principle to as many as you want. So knowing how to distinguish when it's external and internal forces and what that means about whether momentum changes or does not change is good. So the big takeaway from that example is that if you're just looking at the system of one of the balls, momentum is not conserved because you've got a force from outside the system of that one ball, in particular, the force that the other ball applies on it, and that will change the momentum of that system because it is an external force acting on it. But if we widen our scope to the system consisting of both of the balls, then all forces acting are internal or add up to 0 for those external forces of normal force and weight, giving a external net force of 0. And so the momentum of that system is conserved. As far as any problems where you have to apply conservation of momentum, I'm not expecting you to always justify that the net external force is 0 and then say that total momentum is conserved and then do this. Really, your starting point on ones like this is applying that the final momentum of the system is equal to the initial momentum. Same here. Your starting point for solving problems like this is really that. Because if you do that, I know that you know when to use conservation of momentum. Same goes for conservation of energy. If you can identify when you should use that principle, that's good enough for me. You don't need to justify all the, is there a conservative force acting? Is there not a non-conservative force acting? And all that. So all of these examples for momentum conservation are good. And let me see what we had left from this. And this example is good because it is another 1D collision. The rest of the chapter, where you have to separately consider momentum conservation and energy conservation, is stuff on the homework, but is not on the exam. So from there on, the rest is not on the exam. So I want you to know it and be able to use it for homework, but I think it's a little much to test you on. Okay, so that is the quote unquote quick review of the topics covered on the exam. Now open to questions or doing practice problems, whatever you guys want to do. Do you guys want to do anything else?
Well, if it's not a problem with everyone else, we can go over some of the practice exam questions that you may consider the most difficult. So make sure that our understanding is right, since it doesn't show work with the answers.
Okay. Well, does anyone have a particular question from that practice exam? Oh, I guess I'm still actually in that app for this. Does anyone have a question from the practice problems that they want me to go through? There it is. Has anyone looked at the practice problems yet?
Honestly, I didn't look at it yet. I was planning to do it right now after reviewing chapter 5 and 4 and 7.
Okay. 13. Okay. So what is the acceleration of this thing? So anything with a constant, I'd think it would be the other way, but okay. Anything with a non-constant speed, but we've got a 2,400 kilogram satellite in an orbit of a planet. That planet is this zoom thing popping up and out for everyone over and over, or is that just me? I hope that's just me. Anyway, we've got this planet with a radius of 8.8 times 10 to the 6th meters, and a satellite is orbiting 120 kilometers above the planet. So that's our satellite right there. And it's got a mass of 2,400 kilograms. And it's traveling with a constant speed of 6,670 meters per second. So it is in uniform circular motion because it's traveling at a constant speed. So all of our uniform circular motion knowledge applies. So we are given a speed, a radius of this planet, and a height above the planet. Now, you can call these variables whatever you want, but that should tell us something about how we can approach this. Yes, Catherine, great. So the acceleration, we're looking for centripetal acceleration. This is an equation we know for the centripetal acceleration of something in uniform circular motion. So we are given directly that speed v. What about the radius r? What radius should we use?
8.8 times 10 to the 6.
Okay. Is the satellite orbiting this in this circular path about the center of the planet at that distance or at a slightly different distance? Because remember,
Isn't it half that distance?
not half, we're given the radius, not the diameter of the planet.
So it's 120 kilometers.
It is how far the satellite is from the center of its turn, which because the force applying that, the force that is responsible for that centripetal force is gravity, which acts towards the center of that planet, right? Center to center. And so the distance or radius we should use is the radius of the planet plus how far the satellite is from it, because that's how far the satellite is from the center of the planet. Does everyone see that?
Yeah, it's clear.
Okay. No? Okay. Maybe it'll help if I draw this a little bit bigger. We're given that this distance is 8.8 times 10 to the 6th meters. And then the satellite is an additional 120 kilometers above that. But what the satellite is orbiting around, as far as gravity is concerned, is the center of this planet. We said that gravity, even if it's for these larger objects like planets, it acts between the centers of the two objects. And so the force that is being applied on that satellite is the force due to gravity, and it is pointing towards the center of this planet. So the distance we need to use is the distance of the satellite from this center point, which is not the radius of the planet, but the radius of the planet plus how far above the planet the satellite is. That is our overall radius, the distance between the center of the planet and where the satellite is. Yes, 8.8 times 10 to the 6 meters plus 120 kilometers, but that's kilometers. We need to make sure we're using consistent units. So let's convert that to meters. There are 1,000 meters in a kilometer, so that's 120,000 meters. Okay, and so there won't, I believe everything is already in SI units on the exam. Again, I don't emphasize unit conversions on exams. Yep, no problem, Kendra. But now we have everything we need to solve this. It's 6,670 meters per second squared over this number. So 8.8 times 10 to the 6th meters plus 120,000 meters. And that should be, does anyone have that number? Okay, well, I get about 4.98 meters per second squared. So 5 meters per second squared if we're rounding to, this looks like they're doing two significant figures. But again, the numbers are intentionally spaced so far apart that even if you don't worry about significant figures, you should still get the right answer. So if we come over here for answers, we get the right answer. Okay. Catherine, yes, you did, in the sense that that 120 kilometers is so small compared to the radius of the planet that it's not going to change the answer very much. And so, like we said, with rounding, the numbers are so far apart, it doesn't make a huge difference. But in all technical correctness, the radius of the orbit is that radius plus how high above the planet the satellite is. Does that answer your question? Yep. Okay. All right. What other ones do we want to do?
Will there be a question like that on the exam?
Similar.
Okay.
Okay.
Do you think question 14 on homework 6 will be in the exam?
What is that question?
Like, do you want me to read it or?
Yeah, if you could read it out. I don't remember every question on it.
Okay, it is the question that I sent you about the lead on that's on the rope. Wait, let me read you the question. A small lead ball attached to 1.10 meter rope is being whirled in a circle that lays in the vertical plane. The ball is whirled at a constant rate of 3 revolutions per second and is released on upward part of the circular motion when it's 1.3.
Okay. Yes. No, there will not be one like that because I tried to keep the problems from not having multiple concepts at once. They are like, this set of problems is about friction. It's not about uniform circular motion, or this set of problems is about uniform circular motion. This set of problems, and so on and so forth. So they are pretty much independent of each other. And so like that problem that you're mentioning is combining some knowledge about uniform circular motion and conservation of mechanical energy. And so I tried not to do that where we have multiple topics coming into play in a single problem on the exam. They're pretty disjoint.
Okay, so and overall, do you think like if I reviewed all the notes and then just do this question, the practice exam, do you think I will do good in the exam?
Did you see my email about that?
No.
Okay, well, so I said that that's a good starting point. If you're strapped for time, then yes, that's probably your best way to approach it, but it's still going to help you to cover additional things because even with all of these practice problems, there may be something that falls through the cracks if you don't just have it sort of in your head that it is a part of this process. So these problems are pretty representative of what's on the exam, but are not necessarily complete coverage of what's on the exam.
Okay, what about the concepts?
Concepts, I would recommend reviewing the practice sections on Wiley.
Okay, thank you so much.
And quizzes too. So it is possible that something from an old quiz could pop up,
Okay,
or something similar to stuff that was on quizzes.
okay, thank you.
Number 17. Okay. So concrete block with mass 10 kilograms is pulled 7 meters across a frictionless surface by means of a rope. The tension in the rope is 40 newtons, this tension, and the net work done on the block is 247 joules. We want to know what angle the rope makes with the horizontal. Okay, so how I would sort of think about this is I'm seeing something about work. I'm seeing something about a distance moved. I'm seeing something about an angle that we want. What's something that relates all of those? That, right? Or we've been writing it, I guess, slightly different. Okay. But really what we need to know is the net work. And so we need to make sure that we see what all the forces are doing, how they contribute to the overall work done in order to get the right answer on this. So we need the magnitude of that net force. So let's identify what forces are acting on this block.
So the weight and the normal force and friction.
Is friction acting on this block?
Oh, no, and tension instead of friction.
Yep. And that is because it is a frictionless surface. Okay. So we've got tension, which we know what it is. It says it's 40 newtons, but that's all of our forces. So what is the net force acting on this block? Not in terms of numbers, but just in terms of those variables we've got. What's left over when we add up all those forces?
The work done by tension force.
Yes, so the tension force is the net force, right? Because the normal force, or no, excuse me, it's not true. The normal force and the weight in this case don't balance each other because we are we have a component lifting up. This is like on the last exam where it was like, how does the normal force change when we lift up on this thing? So it's not that those forces cancel. It's that they do not do any work on this block because the displacement is across the surface. And it says that's 7 meters. Okay, so Ilham, what you said is right, that the only work done is the work done by tension. And that's because what is the work done by the normal force and what is the work done by the weight of the block?
0.
And why is that?
Because the block is not accelerating in the y direction. What?
Well, that's true, but what I was talking about here, do you see that this component is t sine theta? So really what's happening in the y direction is we've got Fn plus t sine theta minus w is what's equal to 0. And so altogether those do. I just wanted to emphasize that it's not in this case that the normal force and the weight balance out. It's that the normal force, the weight, and this component of the tension balance to give a 0 net force in the vertical direction. So you could look at it as either that the only thing left is this horizontal component of tension, or that we can immediately throw out the normal force and the work, or the work done by the normal force and the work done by gravity, because those forces are perpendicular to the displacement of the block. That's the other case where we said we have no work done by them. So work done by normal force, work done by normal force is 0 joules. And that's because I haven't used this in class, but have everyone seen this before? It's not a flat butt, it's perpendicular sign.
Yeah, I've seen it. I'm familiar.
Okay, and same with the work done by gravity. In this case is 0 joules, also perpendicular. And so we just need to worry about the work done by tension. Tension is the net force here. And so the net work done is the magnitude of that net force, which is this 40 newtons that we said times the cosine of that angle theta. times that displacement. So the cosine part takes care of the fact that it's only the horizontal component of this tension that's going to do any work. That's what we're finding here, that horizontal component. And so if we want to find theta, we just solve this for theta. It's going to be on the other side, we divide through by that magnitude of the tension force and then that displacement. Take the inverse cosine of all of that to get theta on its own. And it said that the net work done is 247 joules. The only force that is contributing to that net work is tension, which has a magnitude of 40 newtons. And then it is pulled, the displacement has a magnitude of 7 meters. And so if we go through that calculation, what do we get? Uh-huh. So we're thinking the answer is A. Go over here, check ourselves. That was 17, 28 degrees. Okay. Does how we got to that make sense to everyone? If not, please let me know and we will run back through it. Silence is not exactly a yes, so I'm not sure if that makes sense or. Okay. Okay. Good. All right. Other. Yeah, that's fine. Okay. Other problems we want to go through?
Can we
Catherine,
take a look at problem 16?
Sure. So Catherine, did that make sense to you as well?
Yes.
Okay. Very good. Okay. So 16, this is just one to kind of show you that ratios are useful in physics. There may not necessarily be something exactly like this, although it is good to know how to calculate the period of an orbit. So the radius of Saturn's orbit around the sun is about 10 times that of Earth, meaning the radius of the Earth's orbit around the sun. So we want to find the period of Saturn. The footnote here is a hint I gave you saying that the number given, meaning that 10 times that of the Earth part, and knowing the period of Earth's orbit around the sun, which is a year, is enough to solve this problem. We don't need to know anything else. And that's what I think is kind of neat about this. The reason is, we'll think about this ratio of the period of Saturn to the period of Earth's orbit around the sun. So picture may not strictly be necessary here, but let's make it more fun. So we've got Earth and then some considerably larger distance for the orbit of Saturn. And so right off the bat, what do we expect about how Saturn's orbit compares to Earth's? Is it bigger, smaller, the same?
Bigger.
Bigger. So it's farther away. The force of gravity is not doing as much on Saturn. It's not pulling. It's not going to be 10 times, and we'll see why. But it is going to be larger by some amount. And so it's because it has to cover a much larger different distance as far as the circumference is concerned, going all the way around this circle. And so it's going to take a lot longer to do that. let's not guess. Let's try and see if we can figure it out doing the math. Oh, it's also not that. So, what is the expression that we found for the period of a satellite's orbit, which we can consider Earth and Saturn to be satellites orbiting the sun? All satellite means is something that orbits something else. So that's distance from Earth's center to the sun's center. And then from Saturn's center to the sun's center. So I'm going to call those RE and RS for future use. What expression do we have for the period of a satellite's orbit?
Is it revolution per second? Oh,
We have a specific formula that tells us the period of a satellite's orbit around another object. So if I go back to which chapter would this be? What would be the relevant chapter here or topic?
Will it be chapter 8?
We're not covering chapter 8 on this exam.
Oh, okay.
The Centripetal Force chapter.
Because
Gravity.
that's a satellite in uniform circular motion. How about that one right there? Okay, that's the only one we have specifically for a satellite's orbit around another planet. So let's see if that will be useful to us. And then we said that if if the satellite's orbiting around another celestial body instead of Earth, we replace the mass of the Earth with the mass of whatever is being orbited. So for instance, with the Earth orbiting the sun, we replaced the mass of the Earth with the mass of the sun here. Okay, so let's apply that over here. So it's 2 pi times the radius of the satellite as far as how far it is from the center of whatever it's orbiting. So from the center of the Earth to the center of the sun is the radius that's relevant for Earth's orbital period. So that's what we call RE. Square root of g times the mass of the thing being orbited, which in this case is the sun. Earth's orbiting the sun, so we use the sun's mass, which we don't know. We could look back at those notes, but like we said, you don't actually need to know it. So let's just keep going here. If you did know it, you could do this calculation, but it would actually take you a little bit longer. So now we've got the period of Saturn's orbit should be 2 pi times the distance of Saturn from the sun, the distance difference between their centers, that distance. And so that has already accounted for that center to center distance. So that's why we don't need to add something else to that radius. So radius of Saturn's orbit, 3/2 over what goes down here.
same GMS.
Because we're also talking about Saturn's orbit around the sun, which is that MS. Here's where the magic happens. Consider this ratio TS over TE. That's 2 pi RE to the 3/2 times that over 2 pi. Oh, I got that flipped the wrong way, don't I? This should be RS, the radius of Saturn's orbit around the sun. This is RE. So do you see that everything but those two radii cancels out? 2 pi over 2 pi, 1 over square root GMS times, or divided by 1 over square root GMS. So that's RS to the 3 halves, or RE to the 3 halves, which by our rules for exponents is the same as this. Okay, and how can we finish out this problem? Distribute what?
The RS with RE multiplied by 10.
So RS, you're saying is RE times 10?
Oh.
Yep, that's the correct thing, right? This is the radius of Saturn's orbit is about 10 times the radius of Earth's orbit. RS is 10 times RE. So if we put that in, RE also cancels. Okay, so we're left with just 10 to the 3 halves power is the ratio of TS over TE. Or if we multiply through by TE, maybe we'll do that over here. TS, the period of Saturn's orbit, is 10 to the 3 halves power times the period of Earth's orbit, which is 10 to the 3 halves times 1 year. Which is, how many years is that?
Is it 31.6?
That sounds about right to me. So to just one significant figure, which is what they're giving us here, 30 years. Okay, so there will not be one like that on the exam where it's like, do this ratio and figure out all these things, do all this algebra from it. It is good to know how to calculate the period of an individual satellite's orbit around something. But I just wanted to include this one because this is where, this is what physicists actually do a lot, is as long as you know the ratios of things, that's really more important than knowing the things themselves. By looking at the ratio of that period of the satellite to the period of the Earth, all that was really different between them was the radii involved. And so we only cared about the ratios of those to some power. So looking at ratios of things can be pretty powerful and can save you a lot of work, because otherwise what you would have had to do is for the period of Saturn, figure out, you put in that G is that 6.67 times 10 to the negative 11. Mass of the sun is whatever the mass of the sun is, I don't remember. And then if you knew the radius of Saturn's orbit, you could plug that in there and find the period of Saturn's orbit, and then see how that compares to Earth's. But by doing a little extra algebra, we actually save ourselves a lot of work on the calculator and trying to make sure we get all that right. And in fact, since we didn't know the radius of Saturn's orbit, all we were given was how it compared to Earth's. The only way we could solve this problem was this ratio. Okay, so don't be concerned that you didn't necessarily think of approaching it this way. I just wanted to introduce you to this concept of these ratios. But what was important for this problem as far as the test is knowing how to calculate the period of a satellite's orbit. Okay. Any other ones we want to go through?
Do you think we have to like write the like in our cheat sheet the mass of like Earth and Sun, the radius and stuff like that?
Those will be given
Oh, okay.
if they're needed.
Okay. Thank you.
Mhm. Okay. Any other specific ones? Because it is good to attempt these too. All right, fair enough, Kendra. Oh, I will say number 6 is one that is very much like what we were talking about with all those different cases of friction on an incline. So I hope that you can solve this one now. How about everyone that is still here gives that a shot and then see what you come up with for the answer.
Can you please zoom in the question?
Yep.
Yeah, thank you.
While you do that, I will be right back.
Oh my gosh, she's so cute.
Here's Gabby.
Oh
Hi.
my god. Hi.
Can everyone see her okay? I can't actually see what
Yeah.
you're seeing. Hi, thank you.
She's so cute.
So this is what you're fighting for. Thank you. To meet Gabby. And also I guess a good grade on the test maybe is something of interest to you, but meeting Gabby I think is pretty nice. So again, if people do well on the test, we'll bring her in to visit maybe right before class one day in the near future. She just woke up from a nap though, so she's a little sleepy. Thank you.
She's so cute.
Trade my degree for her. I'm sure she'd appreciate that. Thank you. Okay, so how are we looking on this problem? And for anyone who's not here live, this is what you're fighting for. Visit from Gabby. Gives very nice kisses and loves people. Loves people. Okay, I'll let you go. Hi, Jocelyn. I'm glad you got to see her. Okay, so how are we looking on this problem? Friction is You're thinking right about it, but friction is not mg cosine theta in this case. So what do we want to do first when approaching a problem like this? What is the first step?
Draw free body graph.
Free body diagram. So let's do that here. So we're interested in what the log is doing. So this is a free body diagram for the log. What forces do we have acting on it? And I guess I'll simultaneously label them on the picture and then on our free body diagram.
Normal force. Perpendicular
Which,
to the-
yeah, perpendicular to the surface.
and the weight
And which way does the weight act?
downward.
Straight down, always straight down. Okay, we've already got our tension drawn in for us. All right, the rope applies that. So that weight, normal force, tension, and anything else?
Friction.
Which way should I draw that friction vector?
Negative side horizontally.
So up the ramp or down the ramp?
Down.
Opposite, good, good. Because that is opposing the motion of the log. And so the log is accelerating, meaning it has to be sliding along the ramp. And so we're dealing with kinetic friction, and it tells us that anyway, but good to know why it should be kinetic. So that's acting down the ramp. So what's a good choice for our axes here?
So the normal force will be the y, the positive y axis,
Okay,
and the kinetic will be the negative x-axis.
there's positive, that is positive. Yeah, I think that's a good choice. A lot of times it's good to save yourself some work to choose the positive direction for the x-axis or whichever direction acceleration is occurring to be in the direction of the acceleration. So we're expecting that the log has an acceleration of 0.3 meters per second. We are expecting that the acceleration should be up the ramp. It's pulled up the ramp, so it'll be convenient to call up the ramp the positive x direction in this case. If it were sliding down the ramp, so there was maybe a pull going that way, then it might be more convenient to call down the ramp the positive x direction. Does everyone see how that can be better? We have less negatives involved. Yes, no, maybe. Okay. And so we said call that plus y, call this minus y. And so before we can move forward, what's another thing we need to do here on our free body diagram?
Draw the y and x component for the weight.
We want to make sure we have all forces or force components acting along an axis because that makes our lives a lot easier. So we want to break our weight vector into components. So I'm going to draw it like this. We got that component and then that component, and those two add together to give the overall weight vector. Okay, and we said if we have an angle theta like that, then that angle between the perpendicular to the ramp and the weight vector should also be theta. And so that's this angle right here, theta. Okay, and I will say this particular example is not necessarily something that would be one single problem. This would be broken up over like 3 separate problems if something like this were on the exam. Okay, so now we are ready to look at our force components along each direction. So we could make our table and do that, but just for the sake of brevity, we'll just list them out. And if you want to go back through and make sure you understand how we got these, then be sure to do that. Okay, so what are our forces acting along the x-axis?
Negative cosine theta, negative W cosine theta,
Mm-hmm.
and
Okay.
friction and tension.
Yep, and so usually since we're given a mass, it's good to go ahead and remember that W has a magnitude of mg. So I'm gonna label that as a negative mg cosine theta, the negative being because it's going towards the negative x direction. And then since we're here, we'll just label this one. Oh, I'm sorry. That's not cosine, that's sine theta, because this side is opposite theta. So sine theta opposite over hypotenuse, that's going to be this side over the length of the hypotenuse. And if you rearrange that, you get that the x component is mg sine theta, with the negative being because it's going to the negative x direction. What about this component? What is this one?
Negative mg cosine theta.
Yep. And again, negative because it's going towards the negative y direction in that case. So you said we've got negative mg sine theta. What else?
The kinetic friction, negative kinetic friction.
Okay, and then maybe someone else, what other forces act along the x-axis?
Tension
Okay, and should it be a plus or a minus? Got a
plus
plus because
it's pointing towards a positive direction.
so you see that once we kind of get used to finding these components, it's fairly straightforward to read them off the free body diagram once you break everything into components. But what should this be equal to? Should it be equal to 0 in this case? Is the block or the log moving at a constant velocity or at rest? Good. Okay, what should it be equal to?
0.3 meters per second.
Give it to me in symbols and variables.
A.
So the net force in the x direction is the mass times the acceleration in the x direction. Okay, so not just A, but we also need M because this is one component of Newton's second law, which says if you have a net force on something, it will accelerate, and we can break that down in two components. So that's the first part. So usually when I'm doing this, I don't even worry about what exactly I'm trying to solve for. I just set up my free body diagram, write out the sum of all the force components, see whether that should be equal to 0 or m times the whatever component, x or y component of the acceleration, and then figure out what it is I'm trying to find from all this. Up until that point, you pretty much always approach this the same way. Draw a free body diagram, label your axes, break into components, and then find the net force along each direction, see if it should be equal to 0 or ma. Okay, so what about the y direction? What forces?
Negative mg cosine theta.
Mhm. And again, the negative is because it's going in the negative y direction. Sometimes I've written that as plus a negative since we're technically adding forces. It just happens to be in the negative direction. But at this point, hopefully it's clear why I'm doing negative sometimes, and sometimes I'm doing positive. All right, what else is there?
The normal force
Plus or minus?
plus
Plus that magnitude of the normal force. Yep, good. And what should that be equal to?
0.
0. So yes, good. Because what's happening in the y direction? Absolutely nothing, right? In the y direction, which is outward from the ramp or towards the ramp, the log's not doing anything that way. It's not moving up or down away from the ramp or towards it because it's sliding along it. Okay. So the sliding part is built into the fact that it is accelerating up the ramp in this case. So yes, this is 0, and you could either think of that as, well, it's MAY, and then it's not actually accelerating, so that's 0, or just say, as far as the direction perpendicular to the ramp, it is not accelerating, and so it is in equilibrium effectively in that direction. Okay, now let's see what it is we're actually trying to solve for. So we want to find the tension in the rope. So we probably want to get tension on its own first and see what we can do from there. Tension is MAX plus that force of kinetic friction plus mg sine theta. Okay, everyone sees how I got that? Okay, good. Oh, MAX. So we're rearranging this first equation, the sum of the forces in the x direction. We found that it's all of these forces should be equal to the mass of that log times its acceleration along the x direction, meaning along the ramp. And if we just rearrange that to get tension on its own, we get this equation I just wrote out. Does that make more sense, Kendra? Okay, good. So we want to get down to the things we know, which I guess I should have labeled a bit earlier, but we've got the mass of the log. We've got the incline of the ramp, it's our theta. We've got the coefficient of kinetic friction. We've got the acceleration of the log, which in terms of our axes is AX. And we want to find the tension in the rope. So we don't know the force of kinetic friction, but we do know that it should be equal to what?
You said what was the kinetic friction? Yeah, 0.8.
So that's the coefficient of kinetic friction. Is that the force of kinetic friction? Because that's what this part is. We don't know that, right? But can we write it in terms of some things we do know more about, is what I'm asking.
It's the mu k Fn.
And so our hope is that, well, it tells us something about the coefficient of kinetic friction. Maybe we'll be able to figure out something about the normal force as well. That's that. Okay, so if we look at this now, we know the mass, it's 200 kilograms. We know the acceleration in the x direction, it's 0.3 meters per second squared. We know the coefficient of kinetic friction, the mass again, know the acceleration due to gravity, and know that angle theta. So the only thing we don't know is that normal force. How can we find it?
Is it mg?
How about we look at our other equation here?
What is 0?
It's not 0, it's balanced by this component of the weight. Right, because if we add negative mg cosine theta to Fn, we get 0. So Fn must be equal to mg cosine theta. And that's what we were finding before too. When we had something on a ramp, the normal force ended up being mg cosine theta. That is effectively always going to be true if you've got something on a ramp, it's mg cosine theta. But there are technically cases where that's not true. Like if I applied a force maybe horizontally like that, that's going to have a component that's perpendicular to the ramp and along it. And so that component perpendicular to the ramp changes how much the normal force has to act back upward to balance all of the pushing downward on the log. But for pretty much all problems we're going to do, if something's on a ramp, the normal force is equal to mg cosine theta, because that's what balances it, makes the object not fly off or sink into the ramp. Okay, and we know the mass of the log, we know the acceleration due to gravity, we know that angle. So we've got all known things. Now, if we put that in for Fn, and so I'm going to factor out the mass just so when we put it in a calculator, you only put it in once, right? Because we just multiply everything else by it at the end instead of multiplying each term by it. And so if we put all of our numbers in for that, can someone tell me what we're going to get? And I'll just go ahead and write them in here. The very little bit of space we have, it'll probably go down to here. So it will wrap around a little bit. 0.3% squared plus 0.8 times 9.8 meters per second squared times cosine 30. So add all of that up, and then plus 9.8 meters per second squared times sine of 30. Add that whole thing. Apply through. That looks good to me. So 2,397 point something. Yep, and so to the two significant figures, that would be that one right there. Okay, now if we check it, which one was that one? There it is. Okay, 2,400 newtons. All right, so that is a more long-winded example. What I would actually have you do on an exam is the first question might be, what is the normal force acting on the log? And so you'd go in and say, oh, it's in this case, because of my free body diagram, it should be equal to mg cosine theta. All right. Now I ask, what is the frictional force acting on that log? You say, oh, well, that's just the coefficient of friction times the normal force. And then maybe a third question would be, what is the acceleration of the log up the ramp if we're not given that? Or in this case, what is the tension in that rope? So it would be broken down into 3 or 4 questions on an exam. Don't worry about trying to get this one done in the span of 1 question worth of time. Okay. Yes, there are, like before, 16 questions on the exam. 5 of them are no work required questions. The remaining ones do require work, and 2 of them require that you draw a free body diagram as part of the problem. And there will be a bonus question. All right, well, again, I'm just here as long as people want me to go through problems. Feel free to leave whenever you need to, or just get sick of me. So if people want me to go through others, I will. But again, it is good to practice some of these on your own before I give the answer, because that will help you make sure you understand how to approach it, not just that you're following along as I'm doing. Okay, number 8. All right, Kendra, you could do this one. What do we have? What are we given? What are we trying to find? Okay, yep, we are trying to find period of the motion, the time it takes for 1 complete revolution. Yep. And we can use whatever symbols we want for these. The reason I usually write like that's T, it's because that's what we've used in class. And the idea is once you write in all of the symbols corresponding to these things, you're going to hopefully think of a certain equation that has all those things in it. Good, Catherine. So let's just finish labeling and we'll get to that. So 4 meters per second is the speed, that tangential speed for the rotation, which we call, not quite, but we can, yeah, not quite Kendra, but it is still fairly straightforward. So what do we call this speed that the object is moving around this circle? Just like what variable name do we end up using for that? Not angular acceleration, that is the next section, which we're not getting into. We just use the variable name v. That's the big takeaway, is what variable name have we used for this thing? For something moving at constant speed around a circle, we call that speed v. We could call it whatever we wanted. It's just a variable name. But if we are consistent with what's in the notes, hopefully that'll make you think of a specific equation that links all of these things. And so then we've got, it says a radius. What letter do we use all the time for radius of a circle? Really in any class, but in here we've used it too. Good. And so this is probably the thing you want to do if you have no idea where to start on a problem, is just highlight the things you're given and see if you can think of the variable name we tend to use for that thing. That may spark something in you for what equation links all of them. And so Catherine already got this, but Kendra, can you think of a certain equation that links the speed of a uniform circular motion, the radius of that motion, and the period of that motion? Okay. 2 pi r. So Catherine jumped 1 step ahead to get to how we would solve for that circumference. Yes, it is. So what equation can you think of? Not looking at the one that she wrote, but what equation can you think of that we have just written down in the notes that relates V, R, and T for uniform circular motion? Okay, v squared over r, maybe. So that would be centripetal acceleration. That is true, but we're trying to find the period t. And so that may not necessarily help us do that without, maybe it's a different equation. Yep. It's looking good. So this one. Yep. And so where that previous equation came from is that we're just trying to find the period of that motion. So we want to get t on its own. We multiply both sides by t. That gets rid of the one over on the right. And then we divide both sides by v to get it not with the t, because that's what we want to solve for. We do that, we end up with 2 pi r over v, or 2 pi times 0.25 meters over 4 meters per second. Let's see, what's that going to be? That's 1/4, so pi over 8. I'm just seeing it, how far I can get with this without using a calculator. So over 4 is what is 0.7. So it's possibly so, oh, and units are meters over meters per second, seconds. And so 1.5.7, I'm going to guess that one. Okay, that's what everyone's getting. Good. So it's about 0.4 seconds. And if we round to, in this case, one significant figure, we would end up getting B. Okay, we check. Yep, answer's B. So sometimes when in doubt, just write down all the variable names corresponding to what you're given and what you want to find. See if you can think of an equation that relates those things. But ideally, you will kind of look at it and reason through what it's asking you about physically. You've got something moving at constant speed around a circle. That's uniform circular motion. And so we can find the speed as the distance traveled over the time it takes to travel that distance. The distance an object travels around a circle is its circumference, 2 pi r. The time it takes is what we call the period. And so it makes sense that the speed should be that distance 2 pi r over that time t. But again, when in doubt, see if you can think of an equation that relates those things. Okay, any other questions?
I have a question in note 6,
Okay,
the exercise, the weightlifter.
okay. We'll get to that. Other way. There it is. All right, what is your question on this one?
So for the second picture, why the weight, the force vector is still up? Shouldn't it be down since he's moving his hand down?
So have you ever tried bench pressing or just like lifting a weight up?
Yeah, like I'm trying to imagine it. So when I push it up, okay, that makes sense. The force will be up. But when I'm
Yes.
putting my hands down,
Mhm.
how come like the force is still for the force vector is still up?
Well, say it was down, okay? Then that means that both you and gravity would be pulling down on it. But that, I mean, you could do that. That is something you can do. But for one, you might hurt yourself, break your sternum because you're trying to pull a heavy weight towards you while gravity is also pulling it. But in this case, it's also telling us that he's lowering it at a constant velocity. And so in order for that to happen, there has to be a force balancing out that force of gravity. So for him to be able to lower it at a constant velocity, this is the force of gravity or the weight of the barbell, he has to apply a force equal in magnitude but opposite that weight so that the net force is 0 so that the barbell moves at constant velocity. So you could pull it towards you. It's just one that's dangerous, and it's not necessarily good for building muscle, because what you want to do is spend as much time under that load as possible. So you do really want to have it move at more of a constant velocity, or at least not a very quick acceleration towards your chest. But as far as this problem goes, it's because it says it's lowered at constant velocity, so something has to balance that force due to gravity to give a zero net force.
Okay, yeah. So now that makes a lot of sense, because
Mhm.
when we usually like put our hands down, we're trying like to resist not the weight thing fell on us. So that makes a lot of sense.
Yeah, maybe a good way to think about it too is like, if there is someone who is like trying to, I don't know, lay down on you for some reason, you're like, no,
Oh
do
yeah.
not lay on me. What you're doing is trying to slow them down while gravity is trying to help them fall down. So you're pushing to resist that.
Okay, that makes a lot of sense. Thank you.
Yep. Okay. Well, I mean, I don't want to keep anyone longer than they want to be here. I'm happy to keep going, or call it. But if you have questions, now's the time. Magnitude versus scalar, as in scalar components. Okay, so do you mean like what is a scalar, or a magnitude of something versus a scalar component of something? Okay. So really a good example of that probably is that problem we just did with the log, which is over here. There it is. So there are a few different things we can talk about for vectors. Let's look at that weight vector. W. That is a vector. It has a magnitude and a direction. Magnitude is just its size, direction, which way the vector is pointing. And so the size of this vector is the mass of the object times the acceleration due to gravity. No plus or minus. Implicitly, it's sort of a plus, right? We know it's going to be a positive number. But as far as a direction, it has none, because it's just the magnitude. We're separating out the direction information from the size information for that vector. But we can talk about, for instance, components of this vector along a certain axis. In this one, we chose perpendicular to the ramp and along the ramp as our two axes. So we might draw in these components, but if we had chosen different axes, we'd have different components. So you see how I drew this is drawing two vectors that add up to give this overall vector W. I would call this one WX vector, and this one, or nope, wrong way. We're calling perpendicular to the ramp, Y. So I call that WY vector. We call that WX vector. What a scalar component is when we first started really the whole class, we talked about 1D kinematics. We said that for 1D stuff, the direction of something is baked into its sign, SIGN. If it's plus, it's along the positive direction. If it's minus, it's along the negative direction. But you see what we've done by breaking this vector into two separate vectors along two separate axes is broken it into two 1D things, these vectors that act along axes, like we're used to with 1D motion, something along a single axis. This is that happening twice along two separate axes. And so what a scalar component is the fact that we said this vector component points along the negative x direction, versus positive x. And then this one points along what we call the negative y direction. And so if we have something pointing in the negative direction, we call it a negative, whatever the size of this thing is. So in that case, this wx right here is the magnitude, the size of this vector component. The direction of it is baked into that negative right there. And then for the wy vector, the corresponding scalar component is negative that magnitude, the magnitude of wy, the length of this vector. That tells us how large the vector is and which direction it's pointing. So magnitude is just the size, whether it's the size of a particular component, like g, it's the size of our overall weight, whether it's just a part of it. So like the size of wy is what we saw was mg cosine theta. Size of wx is going to be sine theta. And then separately, we can talk about the direction for things along axes in terms of a plus or a minus. So that's how we convert from a vector description to a scalar description. That's why they do. Yes, so we can go, once we convert from this vector description to the scalar description, what we're dealing with is lengths of things. And really we're dealing with the lengths of the sides of a right triangle. And so the Pythagorean theorem applies. That lets us relate those magnitudes, those sizes, lengths of these vectors, because it says that the length of the hypotenuse is equal to, so W here being the magnitude of that, which we said is also, you can write as mg, square that, is the square root of the length of that x component side plus the length of that y component side. And so that's why we can use Pythagorean theorem with vectors, because really they're just trig with directions. Does that clear things up, Andrew? All right, good. Any other questions? NWR means no work required. So just like on the previous exam, if it says that, that means you don't have to show any work. The only credit is going to come from circling the right answer. Yeah. Okay. Any others? Now, that doesn't mean you're not allowed to write something down. It may help you solve the problem. And in a lot of cases, it will. It's just I'm not checking your work to make sure of anything, because either the hope is that it will be fast enough that you'll see the right answer pretty quickly, or if you're just out to lunch on it, then maybe by luck you'll circle the right answer and you won't get docked for points for work. I will mention, should have mentioned this before, but I switched the weighting of the extra, or of the showing your work and getting the right answer. So on the first exam, it was 40% for showing your work, and you saw how that worked out on that 4-point scale, and 60% for circling the right answer. On this exam, it will be 60% for showing your work, in the hopes that you will show your work, you will write something to get partial credit, even if you miss something. And then 40% for, at the end of all that, circling the right answer. So my thought is that that will improve grades. We'll see how that turns out. But the big takeaway is remember to show your work, because that's what a lot of people lost a lot of points on the first exam. Fair enough. And again, I think I was fairly generous with the partial credit for showing your work. Most people got a 2 out of 4, even if it was just very not the right approach, but they tried something and it was at least comprehensible. A 3 of 4 you can get even if you miss a key step, but you were on the right track. And a 4 of 4 you can get even if you make an algebra mistake and get a wrong answer. It's just, was the process right? It's just you missed a negative somewhere or something. Yep. So I'm hoping this test will go smoother than the first, but definitely be wary of like pacing yourself because it is 16 questions, and don't overthink them. That's what happened on the first exam for a lot of people too, is they were expecting something harder, but the questions are like what we did as examples, like the easiest homework problems, like what we've done here. Granted, some of these were a little harder, like this one with the log, that would be split up into multiple questions. Or like the one with the ratios of the periods of two things, there won't be anything like that. It's just knowing the period of a satellite's orbit. It's good to know. But to me, tests are just a way to like check up and see how things are going at this point in the semester. It's not the point to where I'm like, have you mastered the concepts of physics? That's why the homework is so much harder than the exams, because that's where I want you to figure out the physics. Exams are just like a quick check, like the quizzes are. It's just a bigger check. Okay. Final questions. The poor laptop's going to have some trouble rendering this video. It's going to be enormous, but I think it'll be able to do it. Yep, happy to help. And yep, not a problem, Kendra. So if you do have additional questions on practice problems, again, make your best attempt at them first, because how you learn physics is through some struggle. I can very much say that from my own experience. But once you hit that point where you're just not sure where to go next, then feel free to email and I'll be happy to help steer you along. Yep, not a problem, Ilham. Okay. Well, it looks like that might be it. So you all enjoy your weekend. I know as much as you can with an exam on Monday, but we're not that far behind, and it is my fault. I do not blame y'all at all for that, but I got to keep on track as best we can. So it had to be either Monday or Wednesday, and I can't do it on the same day as the other class that I have, because then I'd have to bring in 5 boxes of donuts all at once. And donuts get heavy when you have to carry them across campus. Okay, any final thoughts, questions on anything? That's a good thought. Okay, well, if there's nothing else, then I'll go ahead and end the Zoom session. And thank you all for attending. I hope that did help with your understanding of some of this stuff. And again, let me know if you have any additional questions. All right, y'all have a good one.